Sí, mira, a mí simplemente no me sale nada. Estoy aquí, Industrial Affiliates. ¿Te está saliendo a ti? Aparentemente ya está ahí. Pero yo estoy viendo el canal en negro. Y entonces cuando me voy y cuando me voy al link que tienes en el Excel, solamente aparece IAP serio, tranquilo. No aparece el chat ni nada por el orden. Ajá. Se ve YouTube Studio, pero no. Se escucha, estoy escuchando el audio.
We are the UPRM Solar Boat, a student-driven solar boating team. The solar boat team is composed of students from electrical, computer, and mechanical engineering. The team has been working on the project since 2014, and we have been competing since 2016 in Ohio. Our main goal is to participate and win the Solar Splash competition. This is an event that happens every year, and it's an intercollegiate solar boating competition. It's a 5-day event where universities can accumulate points in 7 different categories. The last competition was in 2019, where we achieved second place. Out of 1,000 points, we were just about 1.5 points shy from the first place. Here we have an overview of how the performance from our boat has improved since its beginning. On the left, we have our top speed improvements, starting from only 4.5 meters per second in 2016 to our current top speed, which is 12 meters per second, at almost a 3 times performance increase. On the right, we have our endurance speed, which is the high efficiency race of the competition. We started at 2.1 meters per second in 2016 and today our boat has improved to 2.8 meters per second, almost a 33% improvement since the team started. Due to restrictions established by competition rules, the boat must use lead-acid batteries of no more than 100 pounds per bank. So every improvement over the years have been achieved while using the same batteries with 2.2 kilowatt hours of energy. So this is what the team is currently working on for 2021 in order to improve upon the competition's last results. Starting off with a brand new hull, the team designed 3 new hulls with the goal of providing better displacement for high and low speeds. All 3 new hulls and our current hull were tested using CFD simulations and were also 3D printed to scale for physical testing in a fluid dynamics laboratory. After testing, the chosen hull has been manufactured to full scale using CNC machines in order to achieve the desired geometric form as close as possible. The boat's 15-foot long core is made from a dense foam and then laminated with carbon fiber and Kevlar honeycomb panels, reducing the weight from 110 pounds on our last boat to a mere 50 pounds without sacrificing structural integrity. With any significant change made to the hull, new propellers have to be designed in order to achieve desired points of operation. The team has developed a propeller for high speeds and another one for low speeds, using MATLAB and OpenProp as primary tools. Until last year, every propeller had been made by the team on campus using aluminum. We have started experimenting with 3D printer propellers using polymers such as carbon-infused nylon, all for the benefit of faster prototyping at much lower cost. For the steering system, the team is transitioning from a steel Teleflex system to a much lighter and stronger cable and pulley configuration. Of course, a solar boat needs its solar panels. The competition allows for up to a 480 watt configuration. After researching and testing more than 4 solar panel models, we opted for a solar array made by Solvian with 462 watts. Although we tested configurations which had 480 nominal watts, the Solvian array managed to produce more power at higher temperatures than the other brands we tested. Although this has been an atypical semester for everyone, the team is keeping up with schedule by having weekly online meetings and physical testing when needed. These pictures show the new hull with 450 pounds of load, just as if it were assembled with all of the other components. When comparing the old hull versus the new one, preliminary testing showed the new design to have around a 19% less drag than the previous hull at the same speed and weight. There are several other improvements being made to the overall system, such as more precise instrumentation for better data acquisition, a battery research that is made every year, and so forth. On behalf of the team members and professor of the UPRM Solar Boat, we thank you for attending our video presentation. We hope to have given an informative and useful video about our project.
Greetings, my name is Jeremy Alicea, and to those that are watching, I belong to the Solar Autonomous Boat Project. With me are members Fabian Matos and Pedro Madera, along with our advisor, Professor Guillermo Serrano. In this presentation, we will be talking about our progress throughout the semester and the tasks and goals for the next semester. Before going into details about the project, first we must explain what it is all about. Since solar energy has had an exponential growth in its usage, the implementation of autonomous vehicles with this technology has grown as well. With this in mind, the main obstacle these vehicles have is the implementation of a motion control system. Now, for the main objectives of the project, we have set 3 main goals. 1. To develop and manufacture a frame for the autonomous vessel along with performing tests for said vessel and confirm the boat's mechanical behavior. 2. the implementation of autonomous system and its integration with the motion control software. And 3. To design a solar-powered system to integrate it with the autonomous software. With this, I'll leave you with Pedro Madera, who will be explaining the progress made with the design of the boat this semester.
Hi, I'm Pedro Madera. I'll be explaining the design of the boat. The vessel was designed having in mind the following requirements, which are to use Formula 250 foam attached to thrusters and add solar panels. It was used the program SolidWorks 2020 Student Edition to realize the boat, which all dimensions are in the English system of measurements. As a result, we have a boat of 16 inches of height, 8 feet of length, which are 96 inches, and finally 4 feet of width, which are 48 inches. On the right we can see the figure 1, which is the isometric view, top view, back view, and side view of the boat, with all the dimensions in inches. Using the side view as a reference, we can see that the bottom part of the vessel, which height are 8 inches and 2 inches, is made of the material Formula 250, a low density foam. The upper part of the boat, which has a height of 6 inches, is made with EPS foam, which is expanded polystyrene. At the lower left end, which is the color black, are the thrusters on the boat. Finally, taking the top view as a reference, we can see the solar panels, which have a width of 42.1 inches and a length of 20.9 inches. There are 3 of them, each separated by 0.1 inches. In order to determine the minimum volume of buoyancy needed so the boat can float, it was made a free body diagram with the forces acting in the y-axis, which was made with the program diagram.net. There are several forces acting downwards, meanwhile the only force acting upward is the buoyancy. Using the previous diagram, it was developed the sum of forces in the y-axis to determine the minimum volume that the boat needs to float. On the right, we have the figure 3, which is the calculation made with the program MathCAD Prime. Underneath of the figure, there is a legend explaining the meaning of each variable, which V is the minimum volume that the vessel needs to float. As a result of this calculation, we have that V is 1.402 feet cubed. Taking the volume of the catamaran of the SolidWorks CAD, we have 8.45 feet cubed. If we make a comparison, the volume of the catamaran is greater than the minimum volume needed. This means that the boat can float with the applied forces. It was required to search for the center of mass in order to establish where the storage box and the battery will be located. It was used 2 techniques in the program SolidWorks to find the center of mass. First, it was applied the physical property tool. As a result, it gave us the following length: 37.36 inches at the x-axis, 11.64 inches at the y-axis, and negative 24 inches at the z-axis. The z is negative because the vessel is located in the negative side of the axis, meaning it's truly 24 inches. It was verified this fact using the reference geometry and measures tools to have a clear thought where the origin point is located. Now I'm going to leave you with Fabian Mato, which is going to talk to you about the autonomous software.
Thanks, Pedro. The software we will be using is the ArduPilot rover. The ArduPilot software specializes in RC and autonomous vehicles. This version works for rover-type vehicles, but its frame type can be changed to that of a boat. Since rovers use almost identical parameters to a boat, all that is needed to be done is change set parameter, and the additional necessary parameter
4.8 flight controller on computer. This is connected to the GPS and compass, a safety switch, telemetry radio, RC receiver, power module, which in turn is connected to the speed controllers and the Blue Brights T200 thrusters and battery bank. Since the system will be exposed to water constantly, we must secure its components in a compartment within the boat. For this task, the team chose the Altalix waterproof utility box. Within this box, the team designed a platform for the system to rest on. This platform was 3D printed. The platform replaced and stored in the box, and any components that will need to be outside, such as the GPS, would be connected to the design holes. Overall, we can how we find the system. Overall, we can estimates not successful computer science by much for the world. Even though the world can travel large distances, the major goals that teams have to change the operating system of the software and collecting the data with more information. My name is Alberto Rodriguez. I am an electrical engineering undergraduate student. I'll be presenting the research project titled Automated Power Supply for Power Generation using a Power Amplifier, sponsored by SS Instruments. The liaison is Stefan Piwana and Fernando Lopez, and advisor Gladys Dumonroy. The motivation for this research project is that when building a waveform, which can be a time-consuming task, and you have to build multiple or and unique waveforms that may include sinusoidals, rounds, squares, and triangular components, and other types of waveforms. The total number of waveforms can go up to thousands of different combinations to test voltage, temperature, or slew rates. This process will be easier to create, to read, and load integrated waveforms, so there is minimal effort from the user to create all these combinations and use them for testing. The objectives of this research project: the first one is to create an MILAB UBI, or virtual instrument, that facilitates the generation of arbitrary waveforms. This will include sinusoidal waves and squares, trapezoidal, or triangle waves, and randomly sweep through values on each parameter of the waveform. The second objective is to design an analog power amplifier. The third objective is to create a PCB design of this power amplifier. The fourth objective is to automate this process for loading the waveform on the National Instruments PSI function generator, sending the stimuli to the node, and bringing back the output waveform data using National Instruments testing. The objectives that have been accomplished are the VI to generate and create the waveform through the oscilloscope, and also the general power amplifier circuit for PCB. In process is yet to manufacture the PCB, redesigning the VI to be modular in order to easily run such programs in the test. Validation testing for VI waveform generator and PCB board. In this image, we can see the VI, or virtual instrument, the front panel that was created to create or read a waveform in which we can select to be each section sine, sawtooth, pulse, square, round, triangular, or a formula. We can select the dt, which is the time between each sample. When we are done setting each parameter, we can press done and select the file path in which we want to save the waveform. In this second image, we can see below the graph or waveform that was created using this program. As we can see, section 1, which is a sine, section 2, which is a ramp, section 3, it is a DC value of 0, section 4, which is a sine again, section 5, which is a square, 6, a noise, and 7, sine wave. As you can see, we can create
many combinations of different waveforms, or even just one waveform, depending on which one we select. The selection criteria used to select the OPA 552 was that it had to be able to handle a load of 10 microfarads by 2 kiloohms and had a slew rate of 5 volt per microsecond. We calculated the maximum current for the slew rate, which was 25 milliamps. And the selected op-amp is able to handle 200 milliamps and has a range of negative 30 volts to 30 volts. Based on the datasheet, the slew rate of the op-amp is 24 volts per microsecond. On the right hand side, you can see the PCB board design of the power amplifier, which is undergoing some adjustments to reduce trace lengths. The components that are going to be used in this board are through-hole components. This PCB will be manufactured to be able to validate the program of the VI using teststand. In this section, we can see the methodology that is going to be used for future test, which is going to be the features characteristic to be tested and approach and tools necessary, item pass or fail criteria, corrective actions when the test fails, expected data, actual results, and tested results are going to be part of the future testing. Feature/characteristic to be tested. The slew rate, offset, and amplification, using a basic waveform as the test input for the amplifier. The pass-fail criteria is the following. If the output meets the specifications, it fails if the output is outside of the range of acceptance. For the corrective actions when the test fails, the steps are as follows. We will verify the connection to the oscilloscope, verify the PCB connections, verify the wave generator output, correct the acceptance of the error, and verify. To test the OPA 552 will be the following. We'll connect the op-amp PCB to the wave generator, load basic wave into the function generator, connect op-amp PCB to the PSI oscilloscope, observe the output waveform on the oscilloscope, do a comparison with the expected output waveform, then measure the values of the output wave and compare them with their theoretical values, which may be the slew rate, current, voltages, or others. Continuing with the steps for the OPA 552, we'll determine the pass-fail status given by the pass-fail criteria of the current test, make necessary adjustments, repeating the test if it's necessary, continue with the next waves with different amplifications. Once all these 6 tests in total have been declared passed, the power amplifier will be validated. And also, these steps will be the following for the test stand program or sequence with the VIs. This is the end of the presentation. Thanks for your attention. If you have any questions, please visit the link below and stay safe. Thanks.
Hi, I'm Fabiola Robles.
Hi, my name is Rose Sanchez Irizarry, and in this video we will be presenting our project Doppler Effect Simulator.
The topics that will be talked about in this presentation are indicated here. We're going to be talking about the motivation, a little bit of theory, what is the Doppler effect, the objectives and methodology, phase 1 of this project and the expected outcomes. This project is actually phase 2 of a previous one that will be talked about later on. Our motivation came from asking ourselves, how can we use our abilities as engineers to facilitate learning about sound wave properties and the Doppler effect, but not only for K-12 students, but for everyone. Sound waves are longitudinal waves caused by vibrations moving across a medium.
The volume in a sound wave can be represented in a graphical way by the amplitude of a sine wave. The lower the amplitude of the sine wave, the lower the volume will be, and vice versa. The higher the amplitude, the louder the sound will be. The pitch with which we hear the sound wave is defined by the frequency. The lower the pitch, the lower the frequency, and the higher the pitch, the higher the frequency.
The speed of the wave can be calculated using this formula. Here, our source of sound will be the ambulance. Now, as the source moves away from the person perceives a low frequency. But as the source moves towards the person will be experiencing a high frequency. What is the Doppler effect? The Doppler effect is a common natural phenomenon that occurs to all harmonic waves. It is experienced whenever there is a relative motion between the source and observer. The frequency at which the sound is perceived can be calculated using the following formula. In this picture, we can see how the sound waves behaves as the car moves from point A to point B. Did you know that police radars that determine the speed of the vehicle uses this concept? In this case, the speed detector bounces off microwaves in the direction of a moving vehicle, and then detects the waves that are reflected off of it. The waves then are shifted in frequency due to the Doppler effect, and using a formula, the beat frequency between the microwaves and the reflected waves provide the speed of the vehicle. Assuming that the eye is the listener and he is in a static position, when the black dot moves away from the eye, the wavelength of the sound source is shorter than the listener's, but the frequency of the source is higher than the frequency of the listener's. As we keep assuming, the listener remains in a static position. When the dot moves towards the eye, the wavelength of the listener is longer than the source's, while the frequency of the listeners is lower than the source's.
Our objectives revolve around utilizing the MSP430 and Energia to implement a Doppler effect simulator, with the purpose of making the concept easier to grasp for students in the grades K through 12. Our methodology followed the flowchart shown. We firstly focused on learning how to program the MSP430 using Energia and then proceeded to modify the frequency to simulate the Doppler effect. Then we incorporated the 3 buttons that will simulate the different stages of the Doppler effect, as well as a button with an original sound as reference. 4 button functions will be as follows. The first button will be for the actual sound, which will serve as a reference. The second button will be the slow speed, where there is a tiny continual increase in volume and pitch, simulating the sound source approaching slowly and stopping halfway towards the listener. The third button will have the middle speed setting, where there is a fast continual increase in volume and speed, simulating the sound source approaching the listener and stopping right next to them. The fourth button has the fast speed setting, where there is a fast continual increase and decrease in volume and pitch, simulating the sound source approaching the listener and passing them by. For the simulation to have a visual aspect, we will add an LED road that will light up showing the path the sound source has traveled through. Once these aspects have been completed, we will combine them into a display. We chose the MSP430 due to its versatility and capacity to accommodate all the features we will use to create the simulation, since we will be using a programmable gate amplifier in conjunction with LEDs and buzzers, as well as the buttons for the different simulation stages. During phase 1 of our project, we created a GUI utilizing MATLAB, where the speed of the music played changed according to the button pressed. simulating how the music would be heard when the object emitting the sound was static and far away, close to the listener, right in front of the listener, and right next to the listener. On phase 2 of this project, we want to use the lessons learned on the previous phase and apply them to the second phase, which involves implementing the simulation with the MSP 430.
Finally, for our expected outcomes. Once the investigation is finished, we expect to prove that the MSP 430 TI Launchpad can be a significant aid in teaching about wave properties to students from kindergarten to 12th grade. We also expect to have a designed and a physical prototype of the Doppler effect simulator, developed using the MSP 430 TI microcontroller. And for our final outcome, we expect to have an interactive display that creates the complete Doppler effect experience, to later showcase at C3 Tech, a Center of Science and Technology in Caguas.
Hi, I want to take this opportunity to talk about what the team members of Rumbarino have developed. Rumbarino is a multidisciplinary team from the University of Puerto Rico at Mayagüez, who developed its own autonomous underwater vehicle, AUV for short. Our first AUV is called Proteus. Proteus has competed 3 times at RoboSub. The first time it won Rookie of the Year and the Perseverance Award. The second time it won the Perseverance Award again. And the third time it finished 15 out of 72 teams in the competition. Right now we are developing our new AUV called Hydrus. Hydrus is a bigger, more capable UV made to compete at the highest level. These are the team members of Rumbarino.
In the Mechanical Structures Division, we focus mostly on the physical construction of the submarine, designing its structure while keeping buoyancy, weight distribution, material strengths, and future additions in mind. We are currently developing our newest submarine, which will provide a foundation for future additions and capabilities, such as integrating a torpedo launcher, an articulated gripper, or a DVL sensor. It will also circumvent difficulties in the previous design by coating its 3D printed parts in a photo-curing resin to effectively waterproof them. All in all, our new sub will surpass our previous design and give us an edge in the competition.
In the electric division, we are in charge of delivering the power to the different electronic devices in the AUV. In addition, we designed the printed circuit board, or PCB for short, to make the electronic the most modular possible and make it work in the most efficient way, while also reducing the noise on the circuit communication. As a more recent accomplishment, we designed a new PCB that will be in charge of delivering the power to the AUV and make the router into a buoy so it can stay closer to the AUV while eliminating the excess of Ethernet cable. For the future, we expect to keep upgrading our circuits and connection to be even more modular and efficient.
The Embedded System Division is in charge of creating the link between software and hardware. With the use of an Arduino, we receive inputs from the various sensors of the AUV, while sending signal to the thrusters and actuators. Our focus this year is to create a code that controls the gripper and the torpedoes, and potentially be able to maneuver the AUV with a remote control. However, our main priority being the Arduino code and have the sub run with 8 motors.
The Operation Division optimizes work structure. Its purpose is to maintain the team functioning correctly as it grows in scope and in members. The team also leads communication with possible sponsors and maintains them. Recently, we have given a new purpose to our documentation in order to assure the transfer of knowledge to future Rumbarino members. Along with the Business Division, it relieves administrative responsibilities from the team. The Business Division manages the team resources, such as revenue streams, documentation, and inventory, which keeps the team running efficiently. This team is also responsible of finding opportunities to promote Hydrus and STEM fields for students in elementary, intermediate, and high school.
The Software Division in Rumbarino is responsible for developing and maintaining the high-level code for our AUVs, as well as integrating codes from the other divisions into the main architecture. Our most common language for high-level coding is Python. Additionally, we use the ROS library to handle parallelization of processes. Our current goals are to salvage code from our retired AUV and develop a new architecture from the more robust and modular components for our new sub, Hydras. We hope to improve upon the designs and work of past members by working our old code into more robust solutions.
Control Division is in charge to develop control system of our AUV using Python code and Rust. As of now, we are using a PID control system to help our AUV move in different directions. Our challenge is to make all the movement with all the degrees of freedom that our AUV can do. In addition, we are working with our Victoria motors to integrate the pitch, roll, and sway movement that will make the AUV more dynamic. Due to the pandemic, we developed a simulator using Gazebo. This way we can test and verify our code to work properly and have more ways to continue to improve our development and achieve more goals.
Greetings. We are a team of University of Puerto Rico engineering students, and we are presenting today the Earthquake Alarm Project. Our team is composed by Kevin Rivera, Marcos Felix, Jorge Ortiz, and Johnny Santiago. We will each take turns presenting what we did, how we did it, and the results we have obtained in the project. Greetings. I'm Kevin Rivera, the software development lead for the Earthquake Alarm Project. My main objective for this project was to develop the system software and integrate it into a working system. I achieved this by implementing a modular software architecture. With this approach, I was able to add, troubleshoot, or remove pieces of software without significantly affecting the overall performance of the system. This is the system software architecture for the alarm. When the system starts, it initializes the sensors, the peripherals, the communication modules, the data logger, the input and output pins, and the clock. Afterwards, it runs an infinite loop with scheduled events. The first scheduled event is to read the sensor. When reading the sensor, it'll check to see if the reading exceeds the boundary value, which is the sensitivity set by the user. If so, it'll turn on the alarm, log the data into the SD card, notify that a seismic event is occurring, and display that seismic information in the LCD. The other two scheduled events are to change the sensitivity. The user has the option to change the sensitivity via the app or through the system with the buttons. If it changes the sensitivity, it'll display the sensitivity change in the display, and it'll also display it in the application.
Greetings, my name is Jorge Ortiz and I am the hardware development lead for the Earthquake Alarm project. My main objective in this project was to find a way to incorporate our prototype concept into a single working system. This is because we based our initial design in the form of modules, but we wanted the end user to experience a system that is reliable but also that is easy to work with.
One of the first contributions that I made in this project was to incorporate a data logger. This was done so that the alarm have the ability to record important seismic events data, like for example magnitude and time, for later analysis. Because we base our project on different modules, with the help of my colleague Johnny Santiago, we began our research to recreate those modules based on our needs and using a schematic design software. We did this by looking mostly for open source information of schematics, datasheets, but also implemented techniques we learned throughout our years of study on our university. Once we figured out all of the components of our final design, all of them were integrated into a single PCB design, which it is no larger than the size of an average smartphone. Because the system is made to measure an unpredictable event of nature. A power backup system was incorporated in case the main electrical source in the area is compromised.
Hi, my name is Johnny Santiago, and I am the design leader of the alarm case. Now, I will tell you a little about its characteristics. We decided to build our enclosure that separates the circuits from the outside environment with the Fusion 360 program. It has a length of 215 millimeters, a width of 105 millimeters, and a thickness of 50 millimeters. It is made up of two covers, which are connected by a grip configuration and by placing a screw at the top and at the bottom of the case. For the front cover, we made the holes so that it looked good aesthetically and where we could place the LED screen, the buttons, and the LED light. For the back cover, on the outside, we made the holes where we can access the SD card slot, the micro USB port where the system will be powered, the switch to turn the system on and off, a hole to reset the system, and a box to place the battery holders. Inside, we designed some cylinders where the PCB fits perfectly, and a configuration on top of the battery holder box where the buffer will be placed. It was designed for an easy and optimal assembly for its manufacture, being able to assemble everything from above perfectly. And finally, this is how it looks like, fully assembled and put into operation.
Hello, my name is Marcus Felix, and I will be speaking about my role in the project. My role consisted of studying earthquake phenomena, studying the different types of methods used to determine a magnitude of an earthquake, and validating the project. The validation process consisted of using a Quanser shake table to simulate the movements of an earthquake. The earthquake we used in particular was an earthquake that occurred in Northridge, California some time ago. Our steps consisted of first modifying our equations so that they could fit, so that the accelerometer we use can work seamlessly with the equations. Next, we placed our accelerometer securely on the table with tapes and other different methods. And finally, we compared the data between the theoretical data between the accelerometers in the Quanser table with the accelerometers in our device. Then we plotted this information in Excel and see how our runs were going. We calculated different types of data. We calculated percentage errors between MMIs, theoretical and experimental, and we calculated different types of accelerations that occurred for different types of magnitudes of accelerations. And this is the way we validated our project.
Greetings to everyone, my name is Michael Vasquez Nieves. I am currently pursuing a bachelor degree in electrical engineering with a concentration in control system and also a minor degree in business development. I am in my 5th year and I'm going to be explaining the Radio Intelligence and Space Research proposal called the FPGA Accelerated Obstructor Phase Identification. The team has 4 members. The first one is the business contact, Ken Pride, followed by the corporate mentor, Hector Irizarriz, and then Professor, PhD Raul Torres, and finally me, Michael Vasquez. To be more specific, the coronavirus has spread across most continents, affecting the health of thousands of individuals. The World Health Organization recommends the population to wear masks as a protection mechanism against the virus. However, there are people who do not use masks or use it occasionally. This has caused an exponential increase in the virus propagation curve. Currently, there is no technology that can monitor the use of masks in places with a high probability of conglomeration or where they are compulsory. In terms of public safety, recent years have seen an exponential increase in crime globally. Most of the people who commit some kind of crime use a mask to hide part of their face. Currently, there is no advanced system that can identify whether an individual who may commit a crime wears a mask or not. Value proposition. Value proposition is the value or the benefit that differentiates a product from the competition. For this case, there's no technology that can recognize a face wearing a mask. However, establishments hire personnel to monitor the use of masks when entering to the establishment. This solution causes companies to increase their payroll. It doesn't even guarantee that their security protocol will be fully complied. In terms of security, surveillance cameras are used in establishments to have a physical image of the offender. But the individual may cover their face, making the identification process more difficult. The proposed solution seeks to identify whether the face is covered or not to carry out an action. Solution to this problem is to master facial recognition. The research seeks to adapt facial recognition to solve common problems in society. The main objective is to develop a technology that can identify when an individual does or doesn't have a mask that covers part of their face. This could identify people who do not comply with the established security protocol. In the case of public safety, physical traces of potential criminals could be identified. I would like to add that currently, China is revolutionizing the method of identifying people through facial recognition. This type of technology is having a great boom and is undoubtedly the future. Objectives. The research will be divided into tasks that will achieve the implementation of technology. First, a database of multiple individuals who have part or all of their faces covered will be generated. This database will be provided by Raytheon Corporation. The database will be synthetic, which will save time and cost. An algorithm will be developed using MATLAB. The model will be trained to successfully recognize people who wear masks. The algorithm will be executed in an FPGA. Programming will be converted to a VHDL for FPGA compatibility. The results will be simulated using Simulink. If the results are as expected, the implementation parts begin. The prototype will use an AP camera to capture the data and identify individuals who are wearing masks. The project will not be completed until a functional prototype is achieved and all the documentation is completed. The skills required for this undergraduate research are the following: machine learning, computer vision, programming, FPGA, and IP cameras. Requirements. The requirements are the following: use off-the-shelf AP camera fits as inputs to inference models, create models that can perform inference using an off-the-shelf FPGA, and create datasets required to train the models. This is the timeline that sets the dates for each task. This timeline will soon be transformed into a Gantt chart. For December 1st, 2020, we will create a database of individuals with or without mask. For December 15, 2020, we will obtain the use of licenses and the programmable devices. For January 1st, 2021, we will start with the algorithm development. For February 1st, 2021, we will train the model with the synthetic data. For February 15, 2021, we will convert the MATLAB programming into the VHDL language. For March 1st, 2021, we will implement the programming in the selected FPGA. For March 15, 2021, we will simulate the behavior of the FPGA in Simulate. For April 1st, 2021, we will create the prototype. For April 15, 2021, we will train again the model with the real data. For May 1st, 2021, we will complete all the documentation required. The undergraduate research is sponsored by Radio Intelligence and Space Corporation and the University of Puerto Rico at Mayagüez. These are the references of all the images that appear throughout the presentation. Thanks for the attention.
Hello, my name is Sofia Saavedra. I, along with Eduardo Santiago, am a computer engineering student from the University of Puerto Rico at Mayagüez working on this project. I will be presenting our project on the effectiveness of in situ microbiotic observations via an embedded marine operating, sensing, and imaging stereoscope. Dr. Manuel Jimenez is the advisor for this project, along with co-advisor David Repollet. Some of the most important activities that impact our oceans and coastal ecosystems occur in a microscopic scale. Some examples being coral bleaching, competition between organisms, and fluxes of particles to and from the seafloor. However, observing these important events in their natural environments is a challenging task. In this project, we propose observing the attachment of local wild cultivars of benthic algae onto a 3D printed varying topographical growth plates in two ways, in situ or in place and in a lab environment. The goal being to contrast the effectiveness of conducting this algal recruitment experiment with an underwater stereoscope prototype, which will provide in situ monitoring of the surrounding water quality as the establishing algae begins to develop. Data from both methods will be collected and studied at a future occasion in the laboratory while retaining their raw in situ characteristics that were present at the moment of conducting the sampling process. This data can in turn be used to correlate the visual behavioral component of the organisms being observed while taking into consideration how key in situ ambient variables are affecting them. There are two main problems presented in this project. As mentioned previously, some of the most important activities that impact our oceans and coastal ecosystems occur in a microscopic scale. As such, these events are important and of great interest for research. However, one cannot easily replicate the complex and ever-changing conditions of these natural systems in a lab, as organisms lose valuable characteristics once they are removed from their environments. Thus, the only option to fully capture and study these environments reside in situ research. Unfortunately, even though many existing laboratory instruments benefit the researcher in situ or in vitro, few work in the marine environment. Even if the instruments are waterproofed, they represent a cumbersome load on the marine research diver. To solve this, we propose MOSES. The Marine-Operated Sensing Imaging Stereoscope, MOSES, will be a device capable of capturing stereoscopic images with a log of key sensor readings from the surrounding ambient water. The device itself shall be easy to manipulate via scuba diving, in which a researcher places the device over or looking towards the selected sample area. This device will be separated in two units, an optical unit and a sensory unit. The optical unit will be comprised of two microscope cameras to create stereoscopic images, a 3 lightning control mode to capture the image in near-infrared, white, and near-ultraviolet light, and a user interface to control camera and system settings. The sensor unit will include a thermometer, barometer, pH, and dissolved oxygen sensors. The integration of sensors into the microscope is aimed at reducing the percent of human error in experiments conducted in the marine environment, where portable means of imaging and frequent water sampling are needed. By automating part of the sampling procedure and sampling sensory data along with image data, the imaging device can provide a stable means of observing and correlating small sessile benthic organisms in their natural environment without removing them and altering experimental results. The main project objective is to assess MOSES suitability for in situ underwater studies. Reaching such an objective requires two sequential sub-objectives. those being delivering a functional MOSES prototype and performing assessment tests in an underwater environment where benthic algae attachment can be observed. To complete the first sub-objective, our team will need to complete a MOSES prototype that includes a submersible stereoscope that can retrieve microscopic underwater images and environmental data that complements the microscopic pictures. The second sub-objective is performing actual in situ tests with the instrument prototype to assess its fitness for underwater studies. The first phase of this project is aimed at completing the first sub-objective, the delivery of a functional MOSES prototype. First, we will integrate a camera module system consisting of 2 microscopic cameras and a LED light ring. The module will be developed around a Raspberry Pi 4 microcontroller. Second, we will implement a sensory module that incorporates a temperature, pressure, dissolved oxygen, and a pH sensor. This module will be developed around a Texas Instrument TIVA microcontroller. Third, we will implement a user interface to control the camera and sensor modules and offer some camera features such as image capture modes and sensory data retrieval modes. Following, we will implement a communication system between the sensor and camera modules. And lastly, we will integrate the whole system together. Here we can see the global design of the system, separated in 2 modules. As mentioned, the microcontrollers used for this project will be a Raspberry Pi 4 working as the primary controller and a Texas Instruments TIVA Series C microcontroller as the secondary microcontroller. The second phase of this project will be aimed at completing the second objective, perform assessment tests in an underwater environment. We will first compare the data recovered by leaving 2 sample plates exposed to an open water column for a week's time. Plate 1 will be monitored via traditionally available lab equipment, while Plate 2 is monitored with the MOSES prototype. In both cases, the same type of sample plate will be used for both tests and observed for the same amount of time. After, the sample plates shall be recovered from the water and observed to determine the percent of colonization and possible algae types present. Final results will then be extracted based on observations made with both methods. So far, we have succeeded in completing great part of the first objective to create a working prototype. For future work, we will need to encase the final MOSES prototype into its submergible vessel to test underwater. This includes thorough testing before deploying it in an ocean environment. Also, as phase 1 of the project is close to finishing, we must then start phase 2 of the project, the underwater assessment.
If I don't want to make a video like this of myself, I can just make a really
Well, thank you very much for paying attention. We do have time for the photos. It's 5:20. I apologize again once more for the beginning of the session. I hope that you enjoy the videos, and this live stream will be closed in 1 minute. So please, if you have any comments, you can share them in the chat. Thank you very much. I did share the web link. In that web link, you will find a document where you can find all the Google Meets rooms. Please visit our students and share your comments with them. Thank you.